Hi everyone and welcome to yet another session of Webcast Wednesday. So as usual, we'll be having a team of our technical consultants. So whenever you have any question, you're facing any difficulty, you're facing any glitches, or you have a doubt with respect to the topic that has been covered, you can always get in touch with the technical team that is with us today. So my name is Pranav and I welcome you to this session of Webcast Wednesday for this week. So every week we bring to you one new topic which helps you, get much more comfortable with LabVIEW. We have some contest of the week and we have a very good community active discussion that takes place. So, and today I also have I have Rohit Joshi who will be taking the webcast for you this week, and soon he's gonna be online and he will be conducting the session. You will be having two options for your for getting the audio which is there for the webcast. So to maximize your webcast experience, you can either use VoIP, which is over internet. If you're on a slow internet connection and you're facing any lag, you can simply also use the telephone lines which are there. So for those who are attending from India, can simply dialing to the toll-free number 1800-425-4061 followed by the pin 507248 hash. For people who are outside India, can call us on +91 442 followed by the same pin 507248 hash. So we have two audio options for you based on your net speed. You can choose any one of them and maximize your webcast experience. So I'll be passing over to Rohit now. He's the territory manager with Anai India and he'll be taking the topic for this week, which is pipelining in FPGA.
Good afternoon guys, this is Rohit here. Let's begin pipelining with FPGA. Today we are going to talk about pipelining in FPGA. While using FPGA, you might have faced certain timing violations. The time plays an important role in FPGA programming, especially when you are building algorithms in single cycle time loops. Today we are going to discuss a simple method that can improve the timing efficiency of our codes. So let's take a simple example where I am having 4 processors inside my FPGA VI. When I try compiling this code, I get a timing violation error and the compilation fails. The code currently cannot finish executing within one FPGA clock cycle of 80 MHz clock. In upcoming slides, we'll see how pipelining can be used to speed up the code so that it can run using the 80 MHz clock. As you can see here, the delay that is added by each process. You can see a timing violation analysis window on your screens. So we can see that for the path 1, the requirement is 12.49 nanoseconds, which has been missed by 15.10 nanoseconds. So we can see total delay of 27.47. The logic delay is 20.44. The routing delay is 7.03 and so on. So before we move forward to understand pipelining as a method that is used to optimize the timing performance, let's discuss the key terms which are important to understand. So what is throughput? Throughput is the number of cycles between accepting a new input. Latency, it is the number of cycles before producing a valid result for the corresponding input. And pipelining is a technique which we can use to increase the throughput or speed of an FPGA loop. So here on the screen we can see one basic example, an example that we see in our day-to-day life. It's a laundry process of washing clothes. A laundry where it takes the clothes for washing and drying in batches. So let us assume that there are 3 activities involved in the entire process. Activity A is preparing and loading, which takes 2 minutes. Activity B is washing and drying, which takes 25 minutes. and activity C, unloading and cleaning, which takes 3 minutes. Now the total time taken for any batch to process, that is a batch of clothes to get washed and dried, is 30 minutes, which is our latency. And after we get the first batch, we get subsequent batches at an interval of 25 minutes, which is our throughput. Let's go back to the first slide. Throughput is the number of cycles between accepting new input. Here we can accept new input only after 25 minutes. So what if we break the process of washing and drying into different processes and combine them as loading plus washing as one process which takes 15 minutes and drying plus unloading a second process which takes 15 minutes. Now we can see here that the first batch of clothes goes inside and comes out of the washing unit after 15 minutes. Now this batch can be put into the another unit for drying and it comes out after 15 minutes. So every 15 minutes we start getting the new batches. But the time taken for every batch to complete the entire process remains the same, that is 30 minutes, which is latency. But since we have broken up the process, now we have improved the throughput. Now let's make use of the previous example in pipelining that is used in FPGA codes. So pipelining is the process of separating code within a loop and dividing it into different iterations of the same loop. Therefore, the length of the data flow process within one loop iteration is reduced and loop can run faster while executing the same code in parallel. The figure illustrates how the process consisting of A and B can be divided and run in parallel to reduce the length of each loop iteration. Feedback nodes. Feedback nodes are identical in functionality to a shift register that we have seen in the earlier slide and are often preferable from a user standpoint because they maintain a more congruous appearance similar to that in the initial code. The feedback node uses a value wired to the initializer terminal as the initial value for the first iteration of our execution. The feedback node then stores the previous iteration result for each subsequent execution. If you do not wire a value to the initializer terminal, the feedback node uses the default value of the data type and continues building on previous results in the subsequent executions. You can use the feedback node to implement a pipeline and reduce the long combinatorial paths. When you use the feedback node inside a case structure, the feedback node updates data only on clock cycles when the owning subdiagram executes. So this is one basic example of pipelining where we can see that it takes 7 clock cycles to execute this code. 5 for execution of the code and 2 for the while loop. And now here we can see that by using the shift registers, we have done pipelining and now it takes 5 clock cycles instead of 7 to execute the entire code in which 3 cycles are taken for the code and 2 for the loop. So to maintain the look and feel of the original application, we can use feedback nodes instead of the shift registers. Both the codes that you can see in the screen are the same from the functional point of view. So let's move towards pipelining in FPGA. So here we have analog inputs and analog outputs. So pipelining the analog input and output operations drastically reduces the loop period, increasing the sample rate or control loop rate. Because the analog input and output operations both take a long time to run on the FPGA, it is efficient to put them in parallel on FPGA and have them run at the same time. So on the screen we can see that for the first loop it takes 170 ticks for analog input, 2 ticks for scaling, 38 ticks for analog output and 2 ticks for while loop. In total it takes 212 clock cycles. Now in the second block diagram we can see that we are running scaling and analog output parallel to analog input since we have done the pipelining using feedback nodes, and we can see that the clock cycles have reduced from 212 to 172, which is 19% faster. So let us see what is pipelining optimization. So this question often comes to our mind, what to do if our diagram executes too slowly. So in the above figure you can see the longest path is from DIO to the position indicator. Because little is done in parallel, we can perform the operations in the case structures in parallel. So now we can see that it takes 12 cycles to complete this particular code. So what if we shorten the longest path using basic optimizations? So what we have done is, we have replaced these case structures by case selectors and we are running increment and decrement functions in parallel. So let us see what happens. Now we see that we can complete our code. The code executes in 9 cycles. So let us see what else we can do to shorten this path. Okay. Now what we can do is we can use our pipelining and break the code into 2 parts. Now this code executes in 6 cycles. So we have reduced the number of cycles from 12 to 6 now. Now we'll move towards using pipelining in SCTL. So SCTL is single cycle time loop which is limited by propagation delays through the FPGA circuitry. If total combinatorial path propagation takes longer than 1 clock cycle, the compile fails. So what should we do? A combinatorial path is the path through logic between output of a register and input of another register on an FPGA. A register stores data on an FPGA and updates the data on the rising edge of a clock. Long combinatorial paths take more time to execute and limit the maximum clock rate of the clock domain. So long combinatorial paths are typically a problem in single cycle time loops because the logic between the input register and the output register must execute within one period of the clock rate you specify. In the single cycle time loop, the registers within and between the components are removed, increasing the length of the combinatorial path between registers. If the code in the combinatorial path does not execute within 1 clock cycle, LabVIEW returns a timing violation in the compilation failure dialog box, as we had seen at the start of this presentation. So to reduce the length of the combinatorial path, first simplify the logic as much as possible. Once you have reduced the logic to its simplest form, you can further reduce the length of the combinatorial path by dividing the logic into discrete steps and pipelining your design. Now we can see a block diagram on our screen where within this SCTL the combinatorial path is too long for the FPGA to successfully compile. Now here you must reduce the combinatorial path by pipelining the block diagram. Let us see how it is done. Now we can see that the logic is broken. And now we have used pipelining in SCTL. The combinatorial path is now broken into 2 discrete steps, both of which are short enough to run successfully within the SCTL. The application is still optimized for speed and size, and the code still executes at a rate of 1 clock cycle per iteration with 1 clock cycle latency because of the pipelining effects of the data. So now let us understand what is throughput and latency in a high throughput VIs, in the express VIs basically. So most multi-cycle express VIs implement throughput and latency as shown. For this example, configuration of high throughput square root VI, the throughput is 2 cycles per sample and the latency is 8 cycles per through. So two SCTL iterations must elapse before the function can accept a new input. Notice that there are 2 SCTL iterations between this function accepting input A, input B, input C, input D and input E. The function requires 8 cycles from the time it accepts input A to when it generates the valid output A dash and corresponds to A. Notice that 8 SCTL iterations occur between input A and output A dash, input B and output B dash, and so on. This example function requires 8 cycles before it outputs the first valid result. But afterwards, this example function will output a new valid result every 2 cycles, which is the throughput. So let us discuss some of the pipelining caveats. When you implement a pipeline, the output of the final step lags behind the input by the number of steps in the pipeline, and the output is invalid for each clock cycle until the pipeline fills. The number of steps in a pipeline is called pipeline depth, and the latency of pipeline which is measured in clock cycles corresponds to its depth. For a pipeline of depth n, the result is invalid until the nth loop iteration, and the output of each valid loop iteration lags behind the input by n-1 iterations. Let us see how. So now we have the block diagram of the code that we had seen at the start of this presentation, and below that we have a block diagram where we have implemented pipelining using feedback node. As discussed in the previous slide, the above block diagram shows a pipelining with 3 steps. Therefore, the result of the final step is invalid until the third loop iteration, that is I equal to 2, and the output of each valid loop iteration lags behind its corresponding input by 2 iterations. Now, after implementing this pipeline, we can see that the code has been successfully compiled and there is no timing violation error. So let us now discuss a few high throughput math functions. These functions are similar to numeric functions but support higher throughput rates, handshaking terminals inside SCTL, input output registers, and automatic pipelining. The high throughput add, subtract, and 2 fixed point functions are single cycle functions. These functions execute in a single FPGA clock cycle. All other high throughput math functions are multi-cycle functions. These functions need more than 1 clock cycle to execute. So let us know something more about FPGA high throughput math nodes. There are additional configuration options in most of the high throughput math nodes. For example, you can configure the encodings, word lengths, and integer word lengths of the input and output terminals, whether to add internal registers for function inputs and or outputs, and the minimum number of cycles between 2 successive values of valid input data. Throughput and latency may change with data types. And we cannot generate a graphical graphical code from high throughput math nodes. Let us understand execution mode, throughput and latency in high throughput math nodes. The node generates different code depending on its configuration parameters. The execution mode configuration parameter determines if the node may be placed inside a single cycle time loop or not. Notice there are additional terminals on the node configured to operate inside a single cycle time loop. These terminals are also used for handshaking between upstream and downstream nodes in the same way as shown in the previous section. Notice you can configure the throughput of this node. Changing the throughput adds internal pipelining to the implementation. But this is not the same kind of pipelining as in FPGA, LabVIEW FPGA programming. This pipelining does not increase the latency of the code. I hope all of you enjoyed the topic that we discussed, pipelining in FPGA.
So thanks Rohit for talking about this topic on pipelining. So I guess you would have seen how exactly this pipelining can be used, especially if you're working with these FPGA applications. So whenever you're seeing a timing violation, you want to optimize your code which is there inside the loop, you can use the pipelining technique and reduce the time that is going to be taken by each iteration. So if you have any questions, we are going to be online for some more time. You can simply ask us the questions. The contest for last week could not be uploaded online, so that's going to be the same contest for this week as well. So this is a question. It will go live definitely by tomorrow. So give it a shot, and for all the winners, there's going to be some special discounts on the CLAD. So thanks a lot for attending. I'm going to be online for some more time. So if you have any question, do feel free to contact us.